Okay, 5.2a, logarithmic functions and properties of logarithms. This is quite a long section. I don't know why they didn't spread this a little bit out a little bit more, but we just dealt with exponential functions, and now we're into logarithmic functions. And if you remember, we had talked about inverses, gosh, back in 4.3. That's actually not a loon calling, that's my text notification. But anyway, a lot of people think it's a wolf. Weird. Okay. So the inverse of a function is a second function that undoes what the original function did. So what we talked about earlier is like the inverse of 1 over 3 is 3 over 1. So anyway, that's what we use. Addition, subtraction, they undo each other. Multiplication and division undo each other. So for example, 2 times 3 equals 6, but if I divide by 3, I get 2. So it undoes my multiplication of 3 and gives me back what I started with, my 2. So that's what I mean when I say it undoes what I did. I don't even know if that's a word. All right, so anyway, hopefully you've got some experience with logarithms, and this is just going to be a review. But one of the key things is a logarithm, we'll just shorten it to log, is an exponent. Okay, so if I have 3 to the x power equals 9, what I'm looking for is what number can I put up there to give me a 9. Okay, and that can be written in what's called logarithmic notation. And what that looks like is that, which says, what number can I put in here for x that when I take this 3 and put that number there, I get a 9. Okay, so anyway, this is the exact same thing as this, just written in a different notation, and we will be practicing some of this shortly. So this is called the base. This is called the exponent. And we will keep going here with this. I don't want to just get so far off the track that I get overwhelming, but let me show you what we have done before, and it is called exponential form. We have written things this way. So basically 9 equals 3 squared. Okay, so I'm just using letters instead of numbers. What we're going to be doing is using a different format called a logarithmic function, and this same thing right here can be switched to be written like this. That's a little subscript like that. These two are the same thing. One is just written in logarithmic form, and one is written in exponential form. Now you can tell that this is in logarithmic form because there's this word log there, and this is exponential because it has an exponent. This is not an exponent on the b. It's log subscript b with an x next to the same size as the log here. So don't think that this is an exponent on the b, because it is not. All right, so those are our two forms, and so let's go and do a little bit of practice on switching between those two forms. All right, so I'm going to see if I can make this smaller here, and let's go ahead and try one. 3 squared equals 9. Okay, that's written in exponential form, so let's go ahead and write that in logarithmic form using this right there. Okay, so that being the case, we are going to write log. Whoops, if I can get my pen to work. Log. And what goes as a subscript here? Well, the base does. Okay, the one with the exponent. So this 3 is going to go down here. And then I look, let's see, I need an x. Where's the x is there. It's the number all by itself. So that number is going to go there. And what is my y? Well, it's got to be the only one left, right? It's the one that in the exponential form is my exponent. So we will put a 2 there. So what this says is that my base to the exponent of 2 equals 9, which is what that says. Okay? Log base 3, 9 equals 2. And this 9, and one of the things they call this 9 is an argument. Not really sure, but that's what that number by itself is called. Okay, so b, we're changing that to logarithmic form. So my base is a 4, so I'm going to put log, and my base is going to be down there, and my 1/4 goes here, and that equals my exponent, -1. Okay, so that's all we're doing. We're taking the 3 parts, the base, the exponent, and the argument, and switching them around here. Okay, to the base, the exponent, and what we've got here. And I guess this isn't the argument, this is the argument. So anyway, we just put them in different places. So if it helps to kind of take this, 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 there you go. Okay, and you do the same thing with C and D. I don't think C and D are any more difficult than what we've done. It's just you've got some letters there you're using instead of numbers, but that shouldn't be any problem. In fact, let's just do D while we're messing around with this here. D says that we have x equals 3 to the y power. So write log, put the base here, put the x here, and put the variable or the exponent at the end. Okay? So if you are converting from this back to this, exact same thing, you're just looking at an example. Like if you keep example D there, it makes it real easy for you to go ahead and switch things around. Or if you want to use what I have over here on the left, you can do that too. So if we have log with the base 2 here, okay, knowing that that's the base is going to be my big number, so we're going to write 2, that's my exponent, and then the only other thing left is my 16. So I just switched it from logarithmic form to exponential form. So part B, it doesn't really matter what the numbers are. 0.0001 equals -4. Okay, so I'm going to go 10, because that's my base, to the -4th power, and that's going to equal this here. Okay, so that takes us to example 3, where we're going to start evaluating logarithms. And let's see if I can get some of this stuff out of here. All right, so evaluating logarithms. It says for A, they want us to take y equals the log with a base 2, and they want us to write it in exponential form. So 2 to the y equals x. Okay, not much to that. Part B says use the exponential form that we have here to find y when x is 8. So 2 to the y when x is 8. Okay, so what they do here is they don't really give you too much information here. One of the things that, well, now let's not even go there. They just want you to look here and say, okay, so what number can this y be? Well, what times what I mean, how can I get from 2 to 8? Well, 2 times 2 is 4. If I take it times 2 again, that gives me 8. So it must be 2 to the third power equals 8. So therefore my y must equal 3. Okay? There is a method to do this when they're not this easy and you can't see it so obvious, and that's what I was thinking about going into, but I think I'll wait because I think the book will go into that later. And we'll just keep going over some of the stuff that's a little more elementary, just to kind of get your feet wet on what's happening here. So here, I'm sorry, let's throw that out and let's do C. I threw D in there. 2 of 8. So what that means is, what number can I put on 2 to give me 8? And that number again is 3, just like I did up there. Okay, so let's go to D. D is that one that looks a little hairier, but it's really not. You just use, I mean, we're using a fraction instead of a regular number. So 4 to what power gives me 1 over 16 is what it's asking. Well, I know that 4 with a 2 on there gives me 16, but look, the 16 is in the down there, so it's going to have to be 4 to the negative 2. Because, remember what I said about the negative a long time ago? 4 squared equals 16. But if I put a negative there, that means I want to put the 16 in a different place. I want to put it in a wrong place, really. So 4 to the negative 2 is 1 over 16. And that's how I would do that. And I'm assuming you can do E, and we will just keep going. I'm going to skip the graphing logarithms right there. You can look at the figure 5.15 on some different things on logarithms, and those are things that you might want to put in your notes as far as to determine things on logarithms. One of the things I want to go over here, and let me just take a picture of this real quick. And this is true of logarithmic functions. Okay, so if we have a logarithmic function, the y or x-intercept is 1, 0. So it will cross at 1, 0. The y-intercept is none. It does not. This does not cross the y-axis. This one doesn't, and this one doesn't. But notice both of these go through 1, 0. That's always the case. The domain is, or the numbers for x are going to be all numbers greater than 0. Okay, we don't go over into the negative section here on the x's. The range, the y value, can go to infinity negative, infinity positive, but not with x. X can't be less than, or it can't even be 0. It has to be a number bigger than 0. Vertical asymptote. Vertical asymptote basically means at what vertical line does this number here get closer and closer and closer to, but never quite touches it, never reaches it, and that's called an asymptote. Okay, so when you are doing these and you come up with a vertical line where the graph does not cross it, that is the asymptote. Okay, so let's get rid of that, and let's go into some common logarithms, and then we'll get into some natural logarithms. We've already talked common logarithms when I've used this here, a log, and when it has a base of 10. Okay, so what I had mentioned earlier is that an exponent, or a logarithm, is an exponent. Okay, so let's look and see what we've got here when we're talking about a log with a base 10. Okay, so what I'm looking for is a number that I can put here that will give me, say, 100. Okay, so I can put a 2 there. Okay, my logarithm is 2. All right, so if I were to write this in exponential form, or logarithmic form, it would be like this. Equals what? X is what it really is, what we would put there, meaning we're looking for that number. So, what number am I going to put on 10 to give me 100? Okay. It could be, what number am I putting on 10 to give me 3.176? Okay. There is a number that I can put in there for x that when I take 10 to that power, I get that. Okay. It's going to be a weird decimal number, but there is a number that I can multiply 10 by that's going to give me or I can take 10 by itself that many times, which is really, really weird to think about it. But let's see what we can find for an answer. And the answer I get for that is 0.502. So 10 to the 0.502 power equals 3.176. Okay, so what logarithms do, they have a base of 10, and here's my base, you're trying to find a number I can put there for an exponent that will give you your answer. Okay, so for 100, it's easy because 10 to the second power gives me 100. So it's kind of like, you know how you have 1x and you don't write the 1 there, you just put an x and you assume that there's a 1 in front of there. It's the same thing with logarithms. When we have log, if there's not a number there, we assume it's a 10. So I may say, what is the log? Like that. There's an assumed 10 down there, but we don't write it because it's assumed. So when you don't see one down there on a log, you know that it's always going to be a 10 because our number system is based on base 10. So we don't put the 10 down there. Okay, so sorry if this is really starting to get a little bit hairy. Hopefully as we get working on these, it'll get a little bit better. So this is 5.2a, and we will start with example 5 in 5.2b.